As we gained little information for knockouts from centrality measures and reduced graphs, we found it is impractical and difficult to locate therapeutic targets using macroscopic properties and features. Hence, we changed our approach to find bridges and local bridges in the network. Bridge is an edge whose deletion increases the number of connected components of the graph. Calling network X bridge function return us some bridges, but all of them were connected to a dead-end node, which isn't meaningful. Eventually, we tested local bridges. A local bridge is an edge such that its removal increases the shortest distance between endpoints to a value strictly more than 2. This microscopic property is also shared by the ideal knockout proteins. To increase the relevance to our target protein, we find all local bridges such that one of their endpoints is in our target cluster, as shown by the diagram. There are 48 such bridges, and we visualize each bridge by 2 red nodes in the graph, and the target proteins by yellow nodes. All interactions between the target and neighbor clusters where the endpoints located are drawn. So as you can see, the network graph presents many promising candidates for bottleneck nodes. For each bridge, we selected the endpoint node in the neighbor cluster and handed it to the biochem team for research. We picked the endpoint node in the neighbor cluster because we want to reduce the chance of picking one of the target's neighbor nodes, since knocking out their direct neighbors would almost certainly disrupt their biological function, which makes our network analysis meaningless. The outcome was successful. The biochem team identified 3 to 4 proteins that were great therapeutic targets. Some of them even have existing literature stating that mutating them would cause our target disease, the Lane syndrome. Finalized top 3 therapeutic targets are COX-24, PET100, and MRF1. It can be seen that the result doesn't closely align with what we expected. Those bridges are relatively weak bridges as they are located between densely connected clusters. Many of the strong bridges, as we saw in previous graphs, are not selected by the biochem team. This illustrates applying maths and domain knowledge are equally important to solve real-life problems, which reinforces that our approach of giving 48 proteins to the biochem team is correct, as the feature that's interesting mathematically may not be as meaningful in biochemical perspective. So trying more options increases the chance of hitting interesting targets.